Recording.
Recording in progress.
Okay. Combustions of hydrocarbons. Now there will be a numerical question based on combustion in your exam as well. So okay. Now hydrocarbons. When we talk about the hydrocarbons, they are made up of like hydrogen and carbon. Hydrocarbons, they burn. When the hydrocarbons burn, depending on what kind of hydrocarbons they are, they produce water and they produce carbon dioxide. If there are some additives in the hydrocarbons and sulfur dioxide or NOx gases, they will be produced. Okay, now we are treating with the pure hydrocarbons at this minute. So we talk about the pure hydrocarbons. Now, when we talk about the hydrocarbons and the organic part of the hydrocarbons, it's in long chain. The nomenclature, the way we actually name the hydrocarbons is, for example, let's say I got hydrocarbons. They're with long 3 chains and they are all single bonded. The empty bits, let's say these are occupied by the hydrogen. Carbon can make 4 bonds and hydrogen can have 1 bond. Okay. Now, this is a structural formula of hydrocarbon. This one, I can write it like the other way as well. There are 3 C's. So C3H, how many H are there? 1, 2, 3, 4, 5, 6, 7, 8. This is propane. If I talk about, let's say, butane, or let's say, let's have a look at butane, pentane. Let's do pentane with 5. So let's say 1, 2, 3, 4, 5. This is the formula for pentane, where penta means 5 and ane means a single bond. So if I rewrite that one, pentane, it's a C5, how many H? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. You don't have to actually count these ones. There is an easy way of doing it. Now, there is a thing called alkane, and there is a thing called alkene. Alkenes, these are single bond. Alkane are single bond, and they have double bond, at least 1 double bond. The general formula for the alkane is CnH2n plus 2, where n is the number of the carbon atoms. Now, for example, if I want to do, let's say, it's octane will have a formula C8H2 times 8 plus 2. So C8H18. So this is a general formula. Now, the one you use high octane in your car, petrol, that's the formula, C8H18. If you want to do pentane, C5H10 plus 2, 12, which is here. Alkene has a chemical formula, a general formula, CN H2N. For example, if I go octene, when you write it, it's N with ENE, which is a functional group, octene functional group. Now, if I want to do octene, it's going to be CaH16. How it's going to work? For example, if I do one simple one, then you can have a look at the other one. So let's say the way it goes is we got the methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and so on. That's how it goes. Now, let's say I want alkane. I want to do butane. Butane is going to look like butane from the alkane group. Butane is going to look like, if I draw that one, it's 1, 2, 3, 4. And all these dendrites, the arms, attached to the hydrogen. If I want to do butene, it's going to look like this, for example. Let me do it incorrectly, and then I will show you how to correct it. So it should have at least one bond, one double bond. Carbon can have 4 bonds. So I can put double bond anyway. So let's say that was a hydrogen. And I want to get rid of this hydrogen. Yeah, let's say, let me put all the hydrogen. And then I just rub the hydrogen, that's not required. This is still butane. I want to convert it to butene. Now, butene has C4H8. Now here, I got 2 extra H's. Yeah, so 2 extra H. So I need to get rid of that one. So let's say I want to get rid of this bond, and I put a double bond here. Now, if I put a double bond here, I get rid of 1 hydrogen. So I still need to get rid of 1. Carbon can have 4 bonds. Let's have a look at this carbon. This carbon is having how many bonds? 1, 2, 3, 4. So this carbon is heavy. Let's look at this carbon. 1, 2, 3, 4, 5. So I need to get rid of 1. So I'm just going to get rid of this one. So now this carbon has 4 as well. Yeah. So now I got C4H8. Okay. Now these are alkane. These are alkyne as well, which have triple bonds. Now, usually, when we have a look at the octane, the one petrol, high octane, when we look at that one, we add some other elements in it, like sulfur for the sweetening process. Sweetening process is a process which reduces the knocking noise in the engine. If you put a kerosene oil in your engine, petrol engine, it will create a knocking noise, like 2 metals striking together. So we want to reduce that one. So we add the sulfur and the other additives so it burns properly. But this sulfur is not good for the environment. Rather, you having carbon dioxide and water, you have the NOx gases and sulfur dioxide gases, which mix with moisture to create an acid rain. So we want to get rid of these bits. Okay, let me just. Okay. When the hydrocarbons is burned with excess oxygen, oxygen is in excess, you get water plus CO2. So water comes out from your exhaust plus CO2 comes out from your exhaust. If your engine is running lean, what will actually happen is, which means there is less fuel, it means you won't get enough power. But if your engine is running excess of fuel, there's one other thing that you will get here. Because the fuel is excess and the oxygen is not excess, so you will get unburned fuel coming out from the exhaust, which is not good, which is waste of fuel. If you have limited, this is when there's an excess of oxygen, you get carbon dioxide. If you have a limited oxygen, when the combustion happens, instead of excess, let's say you have limited amount of oxygen, you will produce carbon monoxide, so CO. Carbon monoxide is dangerous. Yeah, if you're burning hydrocarbons. Hydrocarbons, the wood can be considered hydrocarbons when you're burning that one. If there is no excess supply of oxygen, it creates the CO2, and CO2 actually is odorless, goes in your blood, and it takes oxygen from your blood as well. So silent killer. Okay. Now, the next thing, there are two reactions. One is called the exothermic. And the other is called endothermic. Exothermic is a reaction that gives away the heat when the reaction happens. Remember, energy cannot be created nor destroyed. So the product of after the exothermic reaction will have lower value of the energy. What I mean, let's say burning of wood is an exothermic reaction. Yeah, limited, sorry. So let's say burning of wood is an exothermic reaction. What happens is when you burn the wood, okay. When you burn the wood, this is what happens. The woods, if they are here, for example, they're not going to burn straight away. They're not going to burn. You have to give them some activation energy to burn. So you need to give them some energy, activation energy. And this amount of energy is called the activation energy. You give them some activation energy, so the burning process starts. When the burning process starts, what will actually happen is they will give away the energy. So this side, this is energy of reactant, and then they will burn, and this side is the energy of products. So when you got products, the products will be at the lower value of the energy as compared to the reactant. This is called the exothermic reaction. The endothermic reaction is the reaction that absorbs the energy. Rather than giving away the energy, it absorbs the energy. In endothermic reaction, energy of products, energy of reactant. Let's have a look at reactant. Is lower than the energy of products, because products have higher energy because they absorb the energy. For example, boiling of water. When you boil the water, initial water has low energy. But when you boil it, now the water has high energy. The product water has high energy. So we got the exothermic and the endothermic reaction. Okay, now we got the relative masses. For the carbon, the relative mass is 12. For hydrogen, it's 1 times 2 because it's written as H2. Oxygen is O2, so 2 times 16. Oxygen itself, O is 16, there are 2. Nitrogen is 14, but there are 2 of them, so 2 times that one. So if you want to find the molecular mass, let's say, molecular mass of just, let's say, CO2. There is 1 C, so that's 12 plus 2 times 16. So that's going to be 40. 44? Yeah. So let's say 44 gram, kilogram, or whatever. So you go 44 grams. This is the molecular mass of carbon dioxide. Yeah. Units are either going to be grams or kilograms, depends on that. Now then there is a concept of number of moles. Number of moles. Number of moles is like a total mass divided by molecular mass. For example, let's say I have 36 grams of water. So 36 grams of water. And I want to find out how many moles it is. Molecular mass of water is H2O. So that's going to be 18. Molecular mass of water is 18. Total mass is 36. So it's 2 mole. Yeah. Usually we write like mole as MOL with a dot. Yeah, that's the abbreviation. Okay, so we don't have to make it. Let me just stop that one. Now, air as a mixture, air consists of oxygen and nitrogen. Okay. Now, by mass, the composition is different, and by volume, composition is different. Okay, oxygen is 23.2%, and this is 76.8%. And by volume, it's 21% and 79%. In the question, it will give you either we taking by mass or by volume. When the combustion is happening in your car, we assume, well, the air intake is by volume. So we assume that composition of oxygen and nitrogen. The purpose of the oxygen is to facilitate the combustion. If there is limited amount of oxygen, combustion will be limited and you will get carbon monoxide. Purpose of the nitrogen is to confine the flame. It's confined the flame in that one. Let's say if we have this whole air made up of oxygen, I can just burn the matchstick here and it will just, the fire will go all the way from here to the other end. So it's just like, it will just create a kind of vacuum and you suck all the oxygen in. If there is a nitrogen, if I just burn the matchstick, it will make sure my flame is just confined in that tiny, teeny space. Okay. Perfect. That's done. Now, after that, let's have a look at the combustion equation. Okay, let's say I want to do combustion equation. So this is butane plus excess oxygen. If that's unlimited, you will get carbon monoxide plus water. It's excess, so you get carbon dioxide. Now we need to balance the equation. We need to make sure the equation is balanced on both sides. Now I need to balance the combustion equation. So I have to put, there are 4 carbons here. I need to put the 4 here. But if I put the 4 and there are 10 hydrogen here, so I need to put the 5 here to make that 10. But if I do, amount of the oxygen has increased on this side, which is 13. So I need to put 6.5 here. Now, what does that actually mean? We will do the same one for the octane, but let's say it's butane. Let's find the molecular mass for that one. So this is 4 times 12 plus a 10, 1 times 10, let's do that way. This is 6.5 outside, then oxygen, 2 times the 16. And on this side, there's a 4. We already did the carbon dioxide, which is 44. So I'm just going to put straight away 44. Plus 5, water is 18. Yeah. If you can find me this number, please. Anyone? 48, 58? Yeah. And that one? 6.5 bracket 2, 6.5 times 32. 208. Okay, and carbon dioxide? 176. And water? Okay, what does it mean? If you are burning 56 grams of butane, you need 208 grams of oxygen, and it will give you 176 grams of carbon dioxide and 90 grams of water, either in the liquid or the vapor form. But if you add these two numbers, they should be equal to these two numbers. It's the law of conservation of mass. Yeah, if you add these two, the mass of the product should be equal to the mass of the reactant. If there is a difference in mass, what does that mean? It means there is a nuclear reaction going on because you're converting the mass into energy, which doesn't happen in the combustion. Okay, it's the same. You can have the same kind of thing, same reaction for octane, and you can find out, like, for 1 liter of petrol you burn in the car, let's imagine the density of the petrol is 1, same as water. It's less than that, but let's assume. If you burn like 1 kilogram, how much kilogram of oxygen you are using and how much carbon dioxide you are actually producing. So it's a lot of CO2 you produce by burning 1 kilogram of octane or any fuel. Okay, write this one down. Now, if we have a look at in terms of volume, because the last one we did, it was in terms of the mass. But now if we have a look at the combustion analysis or the equation analysis in terms of the volume, we need to consider Avogadro's hypothesis. Avogadro's, there is a constant in your calculator represented by the NA, Avogadro's constant. It has a value 6.023 times 10 to the 23. Is that 22 or 23? 6.022. So that's 22. Okay, times 10 to the 23. This is a number, Avogadro's number. What does the Avogadro's number represent? If you got like a 1 mole of water, 1 mole of water, remember 1 mole of water is equal to 18 grams of water. And this will have 6.022 times 10 to the 23 number of water molecules. And then if you got, like, say 1 mole, and now let's say we're doing oxygen, 1 mole of oxygen gas. Now, oxygen gas is different than atomic gas. It's actually 16 grams of O2. Not 16 grams. It's 32 grams of O2. If I got this will have 6.022 times 10 to the 23 number of O2 molecules. If I got 1 mole of carbon, let's say for the carbon, 1 mole of carbon is 12 grams. we talk about atomic carbon, it will have 6.022 times 10 to the 23 number of carbon atoms, because this is an atomic form. Yes. So this is the Avogadro's number. Now, if we have a look at this equation, hydrogen plus oxygen gives you water. The first thing I need to do is I need to balance the equation. So I need to put the 2 here and I need to put the 2 here. I can get that one. What does it mean by that? It means I need 2 hydrogen molecules plus 1 oxygen molecule, give me 2 water molecules. Or if I divide the whole equation by 2, I can also write it as H2 plus a half O2, give me 1 water molecule. Now this is in proper ratio. We call this proper ratio as stoichiometric ratio, which means the amount of the reactants, minimum amount of the reactant that need to combine to give you the minimum amount of the product. I can also say that one, I got 1 meter cube of hydrogen, and I can have half meter cube of oxygen, and that will give me, if that's in gas form, or if that's in vapor form, I can have a look. Now, what I'm doing is I'm just copying the number from here, 1 and 1. Now, this one is just 1. It's going to give me 1 meter cube of, let's say, water. Yeah. Okay, how 1.5 meter cube converts into 1 meter cube? So it doesn't follow the law of the mass conversion, but volume conversion is still happening because that water, because they are bonded together, the atoms are closer together, and hence they need less volume. Okay. Let's do one numerical question. We're doing the mass analysis. Let's say we got the carbon. It's complete combustion. So it means oxygen is available in excess and it will form a carbon dioxide. Now, we know it's 12 grams of carbon plus this is 30, no, not 30, 16, 32. Not 32. Oh yeah, 32. If the oxygen is not 18, 16, isn't it? Yeah, so 32. And that gives you 44 grams. So equation is balanced in terms of mass. Okay. Now, if I got 12 grams, it needs 32 grams. 12 grams of carbon need 32 grams of oxygen, and it will produce 44 grams of carbon dioxide. If I say, well, this can be gram or kilogram, doesn't matter. You can put that in kilogram because it's in ratio. Now, let's say I got 1 gram. I got 1 gram. And I want relation between these two. So let's write 12 grams of carbon is equal to 32 grams. It needs 32 grams of oxygen. Yeah. If I say 1 gram, 1 gram is going to be 32 divided by 12 grams of oxygen. Can someone give me answer in decimal?
2.66 recurring.
So 2.66 recurring kilogram of oxygen. I can convert that 1 gram into 1 kilogram. And that will be kilo, because it can be, you can convert in tons, kilogram, because it's the same ratio. If you go 1 gram, it will need 2.6 grams. If you go 1 kilogram, it will need 2.6 kilogram of oxygen. If you go 1 ton, it will need 2.6 tons. So you can, because they are in the ratio, so you can convert that one. Now this is important. The reason is because this gives you by mass, the mass ratio. Now, if we have a look at the volumetric ratio, Now, if we convert that into volumetric ratio, we can do that one as well. Now, if let's say, before we do volumetric, there's one other thing. Now, let's say we got oxygen, but if we look at the oxygen, we can't just extract the oxygen from the air. We know the oxygen in the air in terms of mass. What was the relation? What was the mass? Let me just get the thing back. Volume is 2179. By mass is 23. So by mass in air, you have oxygen and you have nitrogen. Oxygen is 23.2%, and that is 76.8%. Now we got this number, and the other one is 2179. So if we want to find out like how much air we need, obviously this is how much oxygen we need, but we need to find out how much air we need. For the amount of the air, what you need to do is to burn or completely combust 1 kilogram of carbon, it's going to be 2.66 recurring divided by percentage of the oxygen that's present, 23.2%. 23.2% is actually 0.232. So if you divide that one, you will get an answer.
11.4.
To burn 1 kilogram of carbon, you need 11.49 kilogram of air. Out of that one, the only thing we use is 23% of the oxygen. The other 76.8% is the nitrogen, which is not required. Okay, so this is by mass. So this one is the analysis by mass. Now, if you want to convert this analysis in volume, we can convert the analysis in volume. Now, in volume, let me just clear some of the bits. So I just need to clear this bit. Okay. Okay, when we do that in terms of volume, I got one, let's say it's 1 meter cube. I just copy the number from here because they are balanced. 1 meter cube, and this is 1 meter cube, and this is 1 meter cube. Now, 1 meter cube of carbon requires 1 meter cube of oxygen. Yeah, so I don't have to do the second step because it's luckily it was just 1 and 1. Okay. Now we need to find out how much in terms of volume is required. So this is the volumetric by volume. How much volume is required? Okay. Now, to do that one, we have a volumetric ratio. Volumetric ratio is 21 and a 79% of nitrogen. Okay. So if I want to convert that one in terms of volume, I can do 1 because 1 meter cube of oxygen. 1 meter cube of oxygen is present in how much air? So if you divide that one, and that will give you the answer.
4.76.
4.76 meter cube of air. So it's the ratio between oxygen and air. So 1 meter cube of oxygen is present in 4.76 meter cube of air. So this is by volume analysis. If in the question it's asked you for find the volume of the oxygen required, you divide by 0.21. If they ask you to do the mass, you need to divide by 0.23. Yeah, so they are two different numbers. Okay, this is the complete combustion of methane equation. Now we can do the analysis by mass and we can do the analysis by volume as well. So if we do the analysis by mass, now we need to convert the masses. So what's the, this is 16 times, yeah, 2 times, let me do that one. 2 times 16 times 2. This is 44. This is 2 times 18. And this one is 12 times 4. Okay. So it means if I'm doing analysis by mass, it means I got 16 kilogram or gram, let's do in kilogram. 16 kilogram of methane requires 30 to 64. 64 kilograms of oxygen, and it will produce 44 kilogram of carbon dioxide, and it will produce 36 kilogram of water. So this is the complete combustion. Now I want to find out what is 1 kilogram of methane required. So I don't need that one. I want to find out how much oxygen is required and how much air it required. So these two, I don't worry about how much CO2 and water is producing. I need to relate these two things. So to relate this thing, I can say 16 kilogram of methane is equal to or requires 64 kilogram of oxygen is required. Yeah. Which means if I got 1 kilogram of methane needs 64 over 16 kilogram, and that is 4. 1 kilogram of methane equals 4 kilogram of oxygen. Okay, oxygen gas. Okay. Now I got that bit. We can do the other bit as well, but just let's relate these two. Now after I got these two, I need to find out 4 kilogram of oxygen is in how much? So now I got 4 kilogram of oxygen, 4 kilogram of oxygen. How much air? Okay, remember we are doing the mass analysis. So the analysis is the mass analysis for the 4 kilogram. So 4 kilogram, if you want to find that one out, I need to divide that 4 kilogram with 0.232. So if you do, because there is 23.2% oxygen by mass. So if you divide that one, 17.24, thank you, kilogram of air. So if I want to burn 1 kilogram of methane, I need 4 kilogram of oxygen, 1 kilogram of methane equals 4 kilogram, requires 4 kilogram of oxygen, which means it required 17.24 kilogram of air. So if you're burning, methane is the one that we actually use for cooking, normal houses, natural gas supply, it's methane. So if you are using 1 kilogram of methane, you need 4 kilogram of oxygen, which means the air circulation has to be at least 17.24. If it's less than 17.24, you will smell the gas because it will be incomplete combustion. Sometimes what actually happens is because if the oxygen is in short, you will be producing CO, carbon monoxide, which will make you sleepy and dizzy. So, or if it's running super lean, what it means like you will have very little supply of air, which means you will have very little supply of oxygen, which means 1 kilogram of methane is not burning, but you still have your stove on, the pressure is still there, which means you will have something here, uncombustible one, you know, like the one that's coming out in the form of methane, and that will be excess smell. Now, if we do the volume analysis, we got 1 meter cube of methane requires 2 meter cube of oxygen. It gives you 1 meter cube of that one plus a 2 meter cube of water, according to that. Yeah, this water is not water; it's vapors. Yeah, okay. Now, when we actually do the analysis, now we need to find out like how much air, volumetric air we need. So I'm just going to do is 1 meter cube of methane requires 2 meter cube of oxygen. Okay. Now 2 meter cube of oxygen. Straight away we got 2 meter cube of oxygen. Now 2 meters cube of oxygen requires how much air? 2 meter cube of oxygen requires how much air? Okay. Remember, we have equals 21. Yes. So 2 meter cube of oxygen. Remember that 21% oxygen. Okay. 2 meter cube of oxygen is present in 2 over 0.21. Anyone got an answer? 9.52. Thank you. 9.52 meters cube of air, which means 1 meter cube of methane needs, for complete combustion, 2 meter cube of oxygen, which is present in 9.52 meter cube of air. So if you're burning 1 meter cube of methane, you need a 2 meter cube of oxygen, which means the air circulation or the size of the air that should circulate in your house is 9.52 meter cube. Okay, now let's say if we look into complete combustion of sulfur to sulfur dioxide. The reaction is sulfur plus oxygen will give you sulfur dioxide. Now sulfur is 32, and this is 2 times 16, which is again 32, and that will give you 64. So if I do that in grams, kilograms, doesn't matter. So 32 grams of sulfur needs 32 grams of oxygen gas, and it will produce 64 grams of sulfur dioxide. Now, obviously, the sulfur is the one that we're using for combustion. Oxygen is from the air. Now, we use exactly the same method if we are doing the mass analysis or analysis by mass analysis. Okay. So for mass analysis, I'm just focusing on sulfur and oxygen. If they want me to find out how much CO2 or sorry, how much SO2 is being produced, I have to do that and that, yeah? Because I want to find out how much oxygen is required. How much oxygen is required? So for 32 grams of sulfur, we need, let's put equal sign because equals 32 grams of oxygen, which means 1 gram or 1 kilogram of sulfur is 1 gram of oxygen, requires 1 gram of oxygen. Now, in mass analysis, 1 gram of oxygen, yeah, thank you. How much air? Okay, how much air is required? So you're going to do it is 1 divided by 0.232. That will give you how much? 4.31 gram of air. So it can be kilogram, it can be ton. So to burn 1 gram of sulfur, you need 1 gram of oxygen, which is present in 4.31 gram of air. This is by mass. Now, if you want to do by volume, if you want to do volume analysis, now we rewrite the equation again. And the equation is balanced. So 1 meter cube plus 1 meter cube is a 1 meter cube. So kind of you're gonna see, but only here, that thing will change. So 1 meter cube of sulfur requires 1 meter cube of oxygen. Now, 1 meter cube of oxygen needs how much air? 1 over 0.21. Because 21%. And you got an answer?
4.76.
Thank you. 4.76 meter cube of air. Okay, so kind of find 21.23. So yeah, the volume of that one is always going to be higher than that gram. So which means like whenever you get that one, whenever you get the volume of the air, it will be bigger than the grams. If they say like, okay, how much of the nitrogen, if they say like nitrogen, how much nitrogen was there. So what you can do is easy way. You can actually take away this and that. So you can do 4.76 minus 1. That will give you 3.76. Now, when we meter cube of nitrogen. Now, when we do this bit, there are other gases. There is not only oxygen and nitrogen. There is a carbon dioxide. There is helium and others. But the percentage of carbon dioxide in atmosphere is less than, not percentage of carbon dioxide. All other gases is actually less than 0.1%. So we ignore all the gases that are present other than oxygen and nitrogen. So these are two most common gases in air.